Is going to explain simplifying radicals, simplifying roots coming out of the quadratic formula. So we'll do a few little practice problems here without the formula first. So I'm going to do 3 problems on this video just as a review as to how to, just a review of the skill of simplifying roots coming out of the quadratic formula. So I look at a problem like number 1. Notice that I do not have a perfect square underneath the radical. So the way that I'm going to handle this, I'm going to simplify radical 32 as 16 times 2. So I'm going to simplify this piece first before I move on. 16 is the perfect square. Notice that I have a GCF when I compare 6 to 4 to 4. I have a GCF in the 3 key spots. The 2 that's underneath the radical is off limits because it's not really a 2, it's just the square root of 2. So I take the GCF between 6, 4, and 4, and I remove that GCF, and I write my simplified answer like this. Since they all share a 2, I remove a 2 from each. This is the most simplified form of the expression that would, this is the most simplified version of the expression that would be represented by what I started with. This will be the most simplified answer for that. Let's look at number 2, or excuse me, let's look at number 5 on the video. So number 5, I've got 128 underneath the radical. 128 is 64 times 3. 64 times 2 rather, over 6. 64 being the perfect square. Noting that I have a GCF in the 3 key spots, 4, 8, and 6. All 3 numbers outside of the radical, when the radical is in its most simplified form, all 3 of those numbers share a GCF. I remove their GCF of 2, and then my simplified answer becomes 2 plus or minus 4 radical 2 over 3. Let's analyze this result for just a minute. Outside of the radical, I have a 2 and a 4, and they do have a GCF of 2. But then when I compare it to 3, 3 does not have a GCF with 2 and 4. So this would be the most simplified form of the expression that I started with. So it's very important for simplifying purposes that you have a GCF in the 3 spots that I'm circling. And remember, the number underneath the radical is off limits when the radical is in its most reduced form. And let's look at one more problem here from this set. Number 6 has a negative number underneath the radical. In the world of real numbers, and we are studying in the world of real numbers, a negative square root does not exist. A negative square root is not possible. So when you're in an Algebra 1 course, and the domain would be the set of real numbers, this is a situation where you would say no solution. Another appropriate response is non-real roots, which is a topic to study beyond this course. And then you would also have the option to just present the null set symbol. So when you encounter the negative underneath the radical, just simply stop and say that this problem has no solution in the world of Algebra 1 real numbers. Let's look at the problem set on the page before, going into the quadratic formula. And I would like to draw an analogy between perfect squares under the radical and non-perfect squares under the radical. So let's look at number 1 together. Let's identify A, B, and C. Notice that it's already in standard form and set equal to 0. So I can go ahead and identify my parts. Moving into the formula, negative b plus or minus b squared minus 4 times a times c, all of that over 2 times a. So getting through the formula, that gives me negative 10 plus or minus. This is going to be 100 plus 8 over 2. So I have negative 10 plus or minus the square root of 108, and my denominator is 2. So I would simplify this as demonstrated on the previous page. 108 is going to be 36 times 3. The square root of 36 is 6, and I'll move my work to this side of the board. So that means I'm going to have negative 10 plus or minus 6 radical 3 over 2. Noting that I've got the GCF in the 3 spots, I'll put a green dot by the 3 spots. So my simplified answer would be negative 5 plus or minus 3 radical 3. And the 2 in the denominator is going to divide away. So that would be my simplified answer for that. And let's do number 3 together on the video. In number 3, it's not set equal to 0. It is not yet in standard form. So that's my first job. Before I identify A, B, and C, A is 1, B is negative 8, C is negative 20. Moving into the formula, negative B plus or minus. Since B is negative, it introduces a double negative sign. And when I'm squaring underneath the radical, I need to square that negative sign as well. B squared minus 4 times A times C. All of that over 2A. So to clean this up, you would have positive 8 plus or minus 64 plus 80 over 2. And that's going to be positive 8 plus or minus the square root of 144 over 2. And that's going to lead me to, once again, I'm going to move to the other side of the board. This is going to lead me to 8 plus or minus 12 over 2. And I would break this apart. 8 plus 12 over 2, 8 minus 12 over 2. So my 2 roots are going to be 20 divided by 2, which is 10, or negative 8 divided by 2, which is negative 2. So I'm going to just make a little analogy between numbers 1 and 3. And since I'm on number 3, I just want to look at this piece, the square root part. So here I had a perfect square underneath the radical. When you have the perfect square underneath the radical, that means that you could have solved this by factoring. There are factors of negative 20 that sum to negative 8. So negative 10, positive 2. So this would be your old skill, and you now have a different way, or another option for finding the roots or solutions. But when you have the perfect square underneath the radical as you go through the quadratic formula, that's your cue that this was also a factorable quadratic using an old previous skill. Let's compare that to number 1. So in number 1, if I tried to use the big X factoring method, I would be looking for factors of negative 2 that sum to positive 10. That is not possible. So this is not factorable. And then notice that the part underneath the radical was also not a perfect square. So that means that this is not something that I could have solved by factoring. The only way to solve this is by using the quadratic formula.